are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission a million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1,000,000 billion atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball. With this discovery at the time the free world faced a war for survival, it was little wonder the first thought was a weapon. But how to obtain enough material for even a single bomb? Only a small fraction of natural uranium is the U-235 isotope, which will fission in a chain reaction. And to separate enough U-235 quickly enough seemed all but impossible. But the impossible became reality as industry, labor, science, and the military combined their efforts to build Oak Ridge, where enough U-235 was separated to build the first atomic bomb. At Hanford, Washington, another impossible project proved possible when a huge plant was built for the mass production of the artificial element plutonium. This process involves what may be called the furnace of atomic energy, the reactor pile. Here is a structure or pile of graphite blocks. In the reactor are placed rods of natural uranium containing both U-235 and U-238. As U-235 begins to fission, the graphite slows down the free neutrons, and some of them hit other U-235 atoms, keeping the chain reaction going. But others of those slowed down neutrons hit U-238 atoms, and here's what happens. Remember, we said that U-238 wouldn't support a chain reaction. However, it will capture neutrons from U-235 fission and start a process which converts the U-238, first to neptunium, then to plutonium. And plutonium will fission in chain reaction. Thus, the reactor itself is a source of atomic fuel. Besides producing plutonium, the nuclear reactor makes possible two very important peacetime uses of atomic energy. Remember that the chain reaction process in the reactor creates tremendous heat, which scientists have learned how to control. Thus, a reactor may be substituted in many industrial applications where heat is now provided by coal or petroleum. But such uses in the foreseeable future are limited. For one thing, a reactor pile must be shielded to protect the workers around it from dangerous radiation, and this shielding adds tremendous weight. However, an atomic energy power plant has already proved feasible. The future supplying of electric power to entire cities is far from impossible, while nuclear power in locomotives, submarines, ships, and even very large airplanes may all but revolutionize future transportation on land, sea, and air. But perhaps the most valuable byproduct of the nation's reactor piles is radioactive isotopes. Research has revealed that many elements not naturally radioactive became so when placed in a nuclear reactor. And these isotopes, working as tracers with such measuring devices as a Geiger counter, became invisible detectives, aiding the cause of science in many different fields. In agriculture, isotopes are now used to test such things as the effect of fertilizers on plant growth and the proper timing for their use, helping to assure bigger and better yields from tomorrow's farms. In industry, isotopes have found literally hundreds of new uses, such as the automatic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible. In the fields of medicine and biochemistry, isotopes are performing near miracles of diagnosis and discovery. With radioactive sodium, doctors are solving more of the seeming mysteries of heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly simplify operations for their removal. Iodine-131 finds one of many uses in revealing conditions of the thyroid, and there are many more. New ways of using isotopes are being discovered constantly through the tireless work of modern pioneers in such fields as chemistry, metallurgy, medicine, and biology. Truly, the superpower which man has released from within the atom's heart is not one, but many giants. One is the warrior, the destroyer. Another is the engineer, seeking to provide vast quantities of energy to run the world's machines. Another is the farmer, helping to better feed tomorrow's world. Still another is the healer, helping to diagnose and cure the sick. And the last is the research worker, working on in the fields of pure science to reveal more of the mysteries of the universe. But all are within man's power, subject to his command. On man's wisdom, on his firmness in the use of that power, depends now the future of his children and his children's children in the new world of the atomic age.